Thank you very much. So, you know, everybody has said so many nice words to Carlos that now we need to turn to the serious thing and say a few words not only on the very kind character of Carlos, his friendship, his sense of humor and everything, you know, but let's talk about mathematics a little bit, and we have a lot to say about Carlos. So, you know, I could make a very boring talk, you know, detailing a number of papers, number of books, well, many figures, but I think it's not really the point of saying how many books, how many citations, or many friends for sure. And rather, let's discuss a little bit the topic of interest for Carlos. So you all know that Carlos had made various contributions, starting for his PhD thesis on a homogenization problem motivated by fluid mechanics, and that's a constant motivation for Carlos along his research career, that he was very much interested in fluid mechanics. He has also worked on the establishment of new pressure boundary conditions for Navier-Stokes equation. You all know that he has been a leading expert in the theory of block waves, and I will, of course, feel obliged to say a few words about this. Fluid structure interactions, that will be my special choice here. Inverse problem, biomathematics, optimal design. Well, too many to discuss today. So let me focus on just one work because I like it very much. I think it's exemplary of what Carlos has done and what you know, we should all do somehow in applied mathematics, which is this work on the periodic fluid structure interaction. It started with a collaboration with industry and with a very late friend, Jacques Planchard, who was an engineer at EDF. And it was so motivated by a very concrete application. I will say a few words about that. It has a very nice mechanical modeling. Then the analysis is a mixture of homogenization, block wave, and the results are quite surprising. And it yields you know, new inspiration for further research. Maybe I will say a few words in the end about that. So let me focus on this specific example. And if you want to know more about the topic, there has been this very nice book by Carlos, Vanni, and so Jacques Planchard about fluids and periodic structures. Okay, so what is the motivation? So Planchard was an engineer at EDF. This guy was also incredible. I mean, he was working on many, many different things. And one of his topic of interest was the behavior of tubes bundles in a reactor. So here is a sketch of what is a nuclear reactor. You have two important parts here, which is the so-called core, where you have the tubes, the fuel pins. So that's this picture here. So you have very long tubes, typically that's 4 or 5 meters high. This is just one so-called assembly, and you have typically a few hundred of those assembly in this part. So many, many tubes, and those tubes can vibrate. And of course, the vibration is never very good for the structural integrity. But there is another place where you have many tubes, which is, yes, here. This is a so-called heat exchanger. That's where the hot water, which has been heated by the nuclear reaction, exchange its heat with a secondary flow. Then the secondary flow produce vapor, and then you produce electricity with this vapor in some turbines. Okay, so that's really here in this heat exchanger that vibration are crucial to control. And so the motivation was, how do you control those tube vibrations? So those tubes are immersed in water. Huh? Okay, so here is a simple, the simplest one, modeling in 2D. This is a cross-section, so this is a cross-section of your tube. And so you imagine that your tube are placed at some position, and then they are linked to this position by some kind of hinges here, okay? And of course, they can vibrate. You know, there will be a rigidity associated to each hinges. There is a mass per unit of length, of course, for each tube. But then you also have the fluid, which is coupling all those tubes together. And then you look at the vibration of this type of fluid structure. That's another picture which is extracted from a report by Planchard. I will come back to some result of this report. That's more or less the same modeling in a cross-section. Okay? So you have a fluid domain that I call omega epsilon, which is you know, the cross-section of your steam generator or heat exchanger or nuclear reactor core omega. And then you remove all the cross-section of the tube. So it's a perforated domain in some sense. And the simplest model for the fluid is a potential flow. Then you could look at more involved models, but potential flow is already enough. So the potential, I call it U epsilon 0, and so you have the Laplace equation in the fluid domain. At the interface between the fluid and the solid, you have continuity of the normal velocity. So U is a potential, so nabla U is a velocity. Nabla U dot N is Neumann condition, so that's the fluid velocity, which is equal to the velocity of the tube, which is a rigid tube. So R is a vector, a 2D vector typically. And so dr over dt is the velocity, and then you multiply by the normal. So that's the interface condition for the velocity. And then you have the second law of dynamics for a tube. So m times the acceleration plus k, the rigidity due to the hinges, times the displacement r, equal to the only force which is exerted on the tube, which is the integral of the pressure force coming from the fluid on the boundary of the tube. Okay, so that P is pressure. And how do you recover the pressure in a potential flow equation? You recover it through the so-called Bernoulli law, where the pressure is equal to minus rho, the density of the fluid, times the time derivative of the potential plus some constant. This constant does not play any role in this integral because it will be 0, since the integral of the normal on the boundary will be 0. Okay? So you have a potential flow, you have continuity of the velocity, and then you have simply the standard equation of motion for a rigid tube. Okay, so people are looking at vibration, so you don't look for a solution depending on time. You assume that the solution will be harmonic in time, and so you look for some frequency omega epsilon such that the solution will be U epsilon depending only on x multiplied by exponential I omega epsilon t, same for each displacement. Then you can solve explicitly the equation for the tube, and you find out that the tube displacement for the tube number p will be simply this constant here multiplied by the force, the pressure force exerted by the fluid, which is in this case simply this integral of the potential. To simplify the notation, I call lambda epsilon more or less this constant in front of this, and if you replace the expression of the tube displacement by this integral inside the potential equation, you get this eigenvalue problem, which is kind of non-standard eigenvalue problem. It looks like a Steklov-Poincaré eigenvalue problem, but it is not. It has a completely different structure, and so you see that the eigenvalue here is on the boundary condition, but it has a very, very different structure. And let us first, before exploring the structure of the spectrum, let us have some insight of what it is. You could compute, you know, if you're back to this equation for the potential, right? You have a number of non-homogeneous Neumann boundary conditions for the potential if you know the displacement of the tube. And so by linearity, you can superpose elementary solution and compute U epsilon in terms of the displacement of each tube, or the velocity of each tube. And so that's what you do here. For each tube and for each coordinate in 2D, this is a Kronecker symbol, so you take one elementary displacement for the tube number Q in the direction EI, and you compute this potential solution, and then by superposition, U epsilon will be a sum of all those terms multiplied by the velocity of each tube. And so you can eliminate the potential in terms of the tube, right? And if you do this, you introduce a so-called mass matrix, so this matrix M, which is defined by the energy of the potential flow, if you want. And eliminating the potential, you end up with this equation for S is a vector of all tube displacement, right? So it's a very long vector. And you have a simple ODE for this vector S. K and M here are multiplied by the identity. So here it's diagonal if you want. But the mass matrix M, sorry, that should be a calligraphic M here. The mass matrix couples everything together. That is, if you move one tube at some place, then all other tubes will move because the fluid is incompressible, so you have a coupling of this. So anyway, this equation is very nice to have some understanding. If you had put your tubes in vacuum, they will, move independently of the other ones. But because of the presence of the fluid, their motion is coupled, and you have a huge matrix here, which is adding some mass. The fluid, is putting some additional mass to each tube, and so the frequency of vibration will be lowered by this added mass effect due to the fluid. Okay? So that's the typical problem that Planchard was interested in. Okay, so what is the goal? Well, the goal is to compute the frequencies of this coupled system of fluid and structure. The frequencies omega epsilon, which are the frequencies of the real displacement, are computed in terms of those eigenvalues lambda epsilon. And you clearly see that the largest lambda, the lowest are the eigenvalue. And the problem is that typically if you fear earthquakes, you don't want to have your tube bundles that vibrate and in resonance with some earthquake, for example. You don't want this lambda to be too large because you don't want to have too low frequency corresponding to the frequency of an earthquake, for example. So that will be, for example, one motivation is to study if your tube bundle will not have any resonance with some dangerous frequencies. Of course, to do that, you first need to know, because there are many, many tubes, as I told you when I show you this picture here, here there is something like, in this single assembly, something like 14 by 14 tubes, and then you have a few hundred of them. So that's too many tubes to do a direct computation, so you need to find an homogenized limit in order to get a simplified model. So that's the problem, how to find the homogenized limit, to compute the homogenized spectrum, and possibly find a nice formula so that you can do computation for this homogenized limit. Okay, before we do any analysis, let's look at some direct numerical simulation that were done by Planchard. So Planchard took the problem with fixed epsilon and did computation. Okay? So it was a 10 by 10 array, but at that time those computations were probably in the mid-80s. It was probably on some Cray XMP or Cray 1, the first supercomputer. Probably now you can do it on your laptop with 10 more tubes. But here is the result of the computation by Planchard and one of his students. So you see that here on the abscissa, that's the number of the eigenvalues. So you have 200 eigenvalues because you have 100 tubes and 2 directions, so that makes 200 eigenvalues. And then that's the frequency of each of those. And so the first thing that you see is that it should be a discrete spectrum because it's the spectrum associated to an ODE, a finite dimensional ODE, but it looks like being continuous. Okay? So that's the first thing that you can look. Then if you look at the picture of each mode, so let me explain. The small circle corresponds to one tube, and then here this smaller row means that this is the displacement. Okay? So this is the fundamental mode, so that's the lowest, corresponding to the lowest frequency of your tube bundle. And clearly, it's periodic in the vertical direction. Well, of course, you have some boundary effects, but, inside, it's periodic in the vertical direction, but it is not periodic in the horizontal direction. And that was a big surprise. It is anti-periodic, so you see that the sign of the displacement is inverse if you go from one column to the next one. So it is 2 periodic in the horizontal direction, and it is 1 periodic in the vertical direction. This is, for me, the biggest surprise. In particular, at that time, homogenization was more or less in its infancy, and the usual rule was you compute homogenized property by looking at just one single cell. If you do that, you will miss the fundamental frequency, the one which is the most dangerous if you think in terms of earthquake. So that was a big surprise, this one. So he has in this report all modes, so I don't remember what is, if you have very, very good eyes, this will be the number of the mode. I don't remember what it is, but it's not very important. Another surprising thing, and I will come to that again at the end of my talk, is this mode, for example, it's almost 0 inside, and the non-zero components are on the boundary. And so that's the first manifestation of what will be called later on boundary layer modes. So these modes of vibration that live close to the boundary which are almost zero inside. Good. So now what is the analysis? Very old work with probably your first student, Aguirre? First student, René Aguirre. A very nice work, you know. So in a simple case, if you assume that your domain is a cube with periodic boundary condition, then there is no asymptotic process to do, because since it is already periodic, you just apply the block decomposition, and I will tell you a few words about that, and you compute the spectrum by, you know, it's like if you have a constant coefficient PD in Rn, you use Fourier analysis, you compute everything explicitly. So that's the same. So that was the first computation by Carlos and his student Aguirre, but very surprising one again. I will show you some result. Then, later on with Vanni, they did the general case of a domain with some boundary condition, and then you have an asymptotic process. And for some reason, the standard method of homogenization was difficult to apply, and you didn't use that. You use another method that you call the non-standard homogenization process, which is based on block waves, and that I will describe in a few slides. Later on, I joined the team, and we applied standard homogenization, and the big surprise was that the result was different. Okay, so one very nice piece of work here is to understand why the block wave method is different from the homogenization method. And it's really surprising, because if you go to the elliptic case, let's say you think in terms of Schrödinger equation. In Schrödinger equation, the block wave theory is very well established, and that gives you the same result as homogenization. So homogenization is more or less equivalent to block wave theory. There are some small differences for elliptic equation or for Schrödinger equation, but here it's different, and so there was something to understand. So let me explain with a very bad picture. I'm sorry, this is scanned from one of our papers with Carlos. The difference between the homogenization process and the block wave analysis. So in both cases, you start from your real world problem. You know, you have a domain and you have some characteristic length epsilon corresponding to the periodicity in your domain. And the standard homogenization process is that you let epsilon goes to zero, so you end up with your domain omega, where you have, you know, some homogenized equivalent medium, which is equivalent to your mixture and fluid and solid, right? So that's the standard process. In a fixed domain, you let epsilon goes to zero. The process which was introduced by Vanni and Carlos for this problem, the block wave analysis, is different, because you first scale the domain by 1 over epsilon, so that each unit cell becomes of size 1, and then you let the boundary go to infinity. So you end up with a periodic array in the infinite medium, and the boundary are forgotten in the asymptotic process. So you forgot completely about the boundary, and you really look at the details of the unit cell. Here, in some sense, the unit cell is average. Here, it's not average, but you forgot about the boundary condition. So that's the difference. So for elliptic problems, that should give the same limit in some sense, but here in this case, that gives different limit. So I must, you know, I see that François is very excited about block waves. I must at least tell you what is the block wave, transform, and let me give in the simplest setting, which is not exactly the one which is required here, but I don't want to enter the details. I don't want to do too much mathematics, so I just tell you the main theorem, which is for any function in L2 of Rn, more or less like the Fourier decomposition, you can make a decomposition saying that the function u is a superposition of periodic function. U hat is periodic with respect to y, and then you multiply it by a plane wave, like the Fourier plane wave, right? But you restrict the frequency, the block frequency theta, to be, instead of the full space Rn, to just be in the unit cell or the dual unit cell. You know, so the unit cell in the physical space is a unit cube, and because I put 2 pi everywhere, the unit cell in the dual space of the block frequency is again the unit cube of 0, 1 to power n. Okay? So this theorem tells you that any function in L2 can be decomposed as a superposition of periodic function multiplied by plane waves, and the frequency is restricted to just a cube. Okay, and that's an isometry like the Fourier transform. You have a Parseval equality. And so what is the interest of this? What is the interest of this? That diagonalize any differential operator which has periodic coefficient. So if you look at any differential operator with periodic coefficient in the full space, you can reduce it to a family of operators posed on the unit cell with strange boundary condition associated to this plane wave here. Okay, so you can reduce a problem in the full space to a family of problems on the unit cube, which is of course very good, for example, for numerical purpose. Okay, so this was more or less the technique which was applied by Carlos and Vanni, and what did they find? Well, they found that if you call sigma epsilon the spectrum for your original problem, which is, remember, a discrete spectrum, right? Finite dimensional, pure point spectrum. In the end, when epsilon goes to 0, if you look at its limit, so you look at all accumulation point of subsequences in the spectrum, then this limit contains the so-called block spectrum. So what is this block spectrum? This is the union for all those frequency parameters, theta, which are lying in a unit cube, right, of the spectrum sigma theta of this cell problem. Okay, so you recognize the potential equation, but just in one cell. You recognize the eigenvalue condition on the boundary, which, you know, it's more or less the same as the one for the original problem, but just on one cell. And then you have this strange periodic boundary condition, which is that it is not U which is periodic, it's U multiplied by this plane wave, which is periodic. That comes from the block decomposition. So this is a problem in one cell with one cube, so it has only two eigenvalues. Okay, it has two eigenvalues, but they depend on theta. And so when theta varies, you get a spectrum, which is called the block spectrum, because of course it comes from the block transformation. And this block spectrum is part of the limit here. One nasty point is that the inclusion here may be strict, and actually it's very often strict. So you don't have equality here. I mean, you don't have a strong enough convergence, and you cannot expect a strong enough convergence, so that you can say that there is equality, that this block spectrum describes the entire limit spectrum. It does not describe the entire limit spectrum. Okay, let's look at the numerical result of Aguirre and Conca. More or less what they did was they compute this block spectrum, right? And here is a picture of the lowest eigenfrequency, right? And that's the same except that you see it rotated. And so there are two very interesting features in this computation. Maybe let me show you before the second one. Okay, that's the second one. And you see that the minimum of the second one corresponds to the maximum here of the first one. But the interesting features here are that first, the minimal value, so the minimal frequency, is here at this point, which corresponds to, oh, by the way, yes, the two horizontal axes are the two components of theta, the frequency. And so you see that the minimal value is at 10 for, let's say, theta 1 equals 0, theta 2 equal 1/2. Okay, so that's exactly the minimal frequency is at 10, like in the numerical simulation, by something which is one periodic in one direction and two periodic in the other direction. So that's a confirmation of the numerical result of Planchard. But the very surprising thing is that here you have a value 10 to the 10.89, something like this, for the for the zero frequency, which is not continuous. Okay, so here this in Schrödinger equations this will be called a Fermi surface. So the surface associated to the eigenvalue lambda 1 of theta, it's not continuous at 0. You have a jump from this value here, 6.97, to up to 10 to 10.89. Okay, so it's discontinuous. It was so surprising that you told me that Planchard, when he saw the result, did not believe it. And he published it in some internal bulletin at EDF, and he erased those points, saying, no, it's not serious. He erased those points because he said it was an error, the student was not good at all, or whatever he said. I mean, if you have any memory, tell me. But he told me, you know, he told me, you know, I'm ashamed, because then we discovered later on that it was indeed discontinuous. He thought it was an error, but it is discontinuous. Okay? And so that's really, again, a big surprise. And yeah, so that's, again, a big surprise. And that's one explanation or one hint to why it's different from the elliptic case, because in the elliptic case, there is a famous result in the book of Bensoussan, Lyons, and Papanicolaou that tell you that if you look at the elliptic operator with periodic coefficient, you can compute the homogenized coefficient A star by the standard method of homogenization, you know, two-scale asymptotic expansion. You have this homogenized tensor A star. And then you can do something a little bit more complicated, which is to use the block wave theory. And if you look at the fundamental mode, the fundamental frequency, the first eigenfrequency, the smallest one, you compute its Hessian with respect to this block parameter theta, and at the value theta equal to 0, you recover the homogenized coefficient. So that's the main result in the standard case elliptic. Here, the eigenvalue is not even continuous. How can you differentiate it? Okay, so you cannot differentiate it because it's not continuous at 0. So that indicates there must be something different between standard homogenization and a block wave. Okay. Anyway, you see that the first result is that indeed the spectrum is continuous up to this discontinuity point, but still you will find something that looks like a continuous spectrum. It's bounded, so there is no eigenfrequency going to plus infinity as in the elliptic case, right? The minimal frequency is not periodic. It does not correspond to a periodic mode, right? And the fact that you have a discontinuity at 0 means that, you know, what does that mean, theta going to 0? Let's think about theta being a rational, p divided by q. Then this block wave, where you have this strange boundary condition periodicity multiplied by this plane wave, if theta is rational, p over q, it corresponds to something which is periodic of period q. And q then can be very large. So it corresponds to a mode which has a very long wavelength. Very long wavelength, which is, let's say, the q, the denominator in the rational expression of theta. So when theta goes to 0, but is not 0, that corresponds to very long wave length modes, and so they are not converging to something which is periodic. So there is a regime which is very, very strange here that you don't see in the elliptic case that correspond to those theta going to 0. And of course, the story was not ended because it's just part of the limit spectrum. Okay, so what do you do? That was my very small contribution with Carlos, that we apply the standard homogenization approach. And so the difference will be that, you know, we have this displacement of the tube, which is constant for each tube. And so one idea is to interpolate, if you want, those constant displacement for each tube and build a continuous function, S of x, that represent, if you want, the displacement at each tube. And so this is a function from omega into R2. And then that give you a, you know, elliptic problem with a Neumann boundary condition, which is non-homogeneous, but then you can apply the standard techniques. Of course, you will have a corrector that will be purely periodic, no block wave anymore. And okay, that's really more or less standard. Compared to the previous work, that's really more or less standard. And then, of course, you find an homogenized problem that is posed in omega. So here you see the influence of the boundary condition. There was no influence of the boundary condition, the outer boundary condition in the previous analysis. As I told you, the boundary is moved to infinity. You don't see it anymore. In this case here, you see it. So clearly, you find different modes of vibration. And the homogenized spectrum is, again, not standard in the sense that it is not a point spectrum. It's essential. And a priori, it's different from the block spectrum. So the final result was this one. If there exists an homogenized tensor, an homogenized equation, I don't give the details because I don't want to bore you. And of course, again, this homogenized equation admits this homogenized spectrum, which is part of the limit and which is a priori different. I mean, they may have some intersection, but it's by chance in some sense, but they usually they do not coincide. But it's not the end of the story. That is, if you take the union of the block spectrum of the homogenized spectrum, it's not the full spectrum. You need to add another one, which is a so-called boundary layer spectrum. So more or less, it's the spectrum which is associated to modes which are localized close to the boundary. And if you look at a domain which is, let's say, a rectangle, then you can do an explicit characterization of this boundary layer spectrum, and that corresponds to one of the modes that I've shown you from the computation of Blanchard. What is interesting is that the lowest frequency is not attained, that can be proved, it's not attained in the homogenized spectrum, it's really attained in the block spectrum. And so if you were an engineer, you know, applying standard rules of homogenization, you would miss the fundamental frequency, which is really the most important thing here. Okay, and then there has been some further contribution saying that the boundary layer spectrum depends on the choice of the sequence epsilon because it really depends on the way the outer boundary omega cut the periodicity cell, so the value of the sequence is important in this case. Okay, so that's more or less the end of what I want to say. Let me tell you, some words about the truth of the application, because I think it's very important, once you have done a beautiful analysis of a real-world problem, how helpful it is. The truth is that vibrations are not very important for the core of the nuclear reactor core. Why is it so? Well, because for water reactor, in the end, you will say, I want to optimize a network of tubes in order to reduce the possibility of frequency. Well, it's not critical. What is critical for the core is really a problem of coming from neutronics. So for the standard pressurized water reactor like we have in Europe, this was not really critical for the core of PWR. For the steam generator, or the heat exchanger, it is really crucial. I mean, that's one of the most fragile part in the nuclear reactor core. It's this part, because the tube vibrate, but the vibrations are so large that you have shocks between the tube. Okay? And so if you don't take into account shocks, your analysis is limited. And so that's one limit of this analysis, which is purely linear. You should include shocks. But clearly, that's a problem still of very much industrial importance. Well, I have some good news or some bad news. That depends if you like nuclear energy or not. The good news for the mathematics is that there is another type of reactor, which is not very popular, I must say, which is fast sodium reactor, where vibrations are very important because there is a coupling with neutronics. I don't want to enter into the details, but that's a different type of behavior of the neutrons. It's a different range of energy. And so if the tubes are vibrating, you will have some gap. The tube contains, in this case, the nuclear fuel, and so you may have some gap or some concentration of nuclear fuel, and then you may have a coupling, a very strong coupling with neutronics, and that may be dangerous in some sense. So for this type of reactor, probably your work will be, of course, maybe again of interest if you couple it with neutronics. No, maybe it's not a very good news because, those fast sodium reactors, we have very bad memories of Cress-Malville, who never worked very properly, so I'm not sure it's a very good idea to, but okay. Nevertheless, the French Atomic Energy Commission is still thinking about this for the future. We'll see. Nevertheless, here vibration will play a very important role. So with this, I conclude, and Carlos, thank you very much for all your work.
Okay, so it's a pleasure for me to be here, and I would like to thank the organizer for organizing this meeting for Carlos, to have me invited. And I would like also to thank Carlos because his purpose of having such an assembly of friends of him. And so what I think it's a good idea with 60th birthday is the fact that this is a way to get together a lot of old friends. Okay, old in the sense as Jean-Pierre defined yesterday, since of course this shows us, to some of us, that we are on the other part of the barrier. Okay, so thank you to the organizer, thank you to Carlos. I will make, as said Grégoire in his talk, a very boring talk only about mathematics. And I will speak about some, okay, so this is all technology. A semi-linear elliptic problem with a singularity at u equals u. This has apparently no connection with the work of Carlos, but yesterday I was happy when he said in his address at the banquet that Bilbao was a singular point to organize his birthday meeting. So this is a singular equation. So at least there is a contact. Okay, this is a work with Daniela Giacchetti and Pedro Martinez Aparicio. And okay, this work is inspired by essentially two papers. There are many other ones, but Lucio Boccardo and Luigi Orsina on one part, and Lucio Boccardo and Juan Casado Diaz on the other part, they came back to this whole problem in recent years. And they, okay, this was the beginning of the inspiration of our work. Okay, so this is a lecture which is dedicated to Carlos. And now here is the problem. The problem is extreme. Okay, it's simple. This is minus delta U equals F with some variant. Okay. The condition will be, boundary condition will be Dirichlet. This is minus divergence of A gradient U equals F of XU in omega. Omega is an open bounded set of Rn. A is a matrix with L infinity coefficients, which is coercive. So you look to delta is the same. So the only interest in the problem is this term here, and the model of this term is given by that. This is a function multiplied by a constant plus 1 over s to the power gamma, with gamma strictly positive. So this will be a function which is Karateodori, so very well, but in Zemo, this function can explode. Okay? It will not explode if H here is 0, but if this is strictly positive, this will explode in 0. So this is a subilinear singular problem. Okay, actually, this is the model, but any function f which is between 0 and which has a chapeau, okay? The chapeau being h of x 1 plus 1 over s over gamma is allowed. Okay, and in particular, what is important in our work is the fact that this function is not supposed to be decreasing in s. This function here is decreasing in s, so which is very important. But in our work, this is not assumed that this function here is decreasing in S. Okay? So the solution will be non-negative, and this is important also because this means that we do not cross the singularity. Okay, when we began this work with Daniela and Pedro, our idea was to get rid of this condition in the problem and to allow, okay, f not to be 0, okay, all technology, to correct directly on the screen, to pass to a function which is non-positive, and if the function f can change sign, of course, u will change sign, and we will cross the singularity. Okay. Okay. Sorry?
L'électricité.
Je n'ai pas d'électricité.
Tu peux, voilà, en plus, c'est plus en mode. Tu peux le mettre en clair.
Okay, so now I have no. Est-ce qu'il y a quelqu'un qui a un chargeur? Oui. Oui, mais un chargeur all style, hein, parce que.
All style, non, non, non.
Okay. So our hope was to pass through the singularity, but we didn't succeed. So in some sense, okay, this is a variation about the work of Lucio, Luigi, and Juan. Okay, and we are concerned for this problem with existence, stability when you make this vary, uniqueness of the solution, and also, I didn't put that here, homogenization with many small holes with this Dirichlet boundary condition. Okay, sorry. So I will concentrate in this talk on a very simple case, the case where the power gamma is less than 1. And you will understand in 1 minute why. This is not completely different, but looks very different with the case gamma more than 1. Because I will do that, because I will make a very boring talk, and I will go into all the details of the proof. Of course, the interesting case is the case where gamma is more than 1. Okay? So at the end, maybe you will have a flavor of that. Okay, so as I said before, okay, sorry. As I said before, okay, I will concentrate on existence, but the real problem in this problem is to define the solution of that. Okay, why? Because you know this is usually not in h minus 1. Okay, actually it will be in the case gamma less than 1. And so what is the meaning of the solution? What is the meaning of the equation? Okay, this is, in my opinion, one of the main points in any problem of PDE. You have first to understand what you want to look at before of proving the existence. Okay, good. So in the case where gamma is less than 1, fortunately the solution is easy. You look, okay, I give the definition of the solution. U will be a solution of the problem if U is in each one 0. Okay, very good, as usual. U is non-negative, of course, because F here will be non-negative. So by the weak maximum principle, U will be non-negative. And, okay, you need the equation against some test function. The test function will be function in each one 0. For commodity, I take them non-negative, but when you have non-negative and non-positive, you add the both and you have any function. But when V is non-negative, you can define this function f of x u v for every V, okay, positive and measurable. And one of the two requirements of the equation is that this number here is finite. This integral, which could be finite or infinite, is finite, and you have the equation is in the usual sense. So you will say, okay, François, okay, it's like usual, you forget about that, and the equation is as usual. Yes, but this is one requirement, actually, because in general, this has no reason to have a meaning. Okay, so natural definition, and what is very good, it works, and it allows us to prove the existence. Okay, so to prove the existence, what do? As usual, you make an approximation, you make a priori estimate, you pass to the limit. Okay, first step, you make an approximation. So the right-hand side here was not add a singularity. I cut the singularity as height 1 over epsilon. So this is now a bounded function. I get a solution of that. Since this is non-negative, u epsilon is positive, and I want to get an a priori estimate. Okay, what I do, as usual, I take u epsilon as test function, okay, and I get a gradient u epsilon equals f epsilon of u epsilon. Okay, this is less, f epsilon is less than f, so this is less than h1 plus 1 over u epsilon to the gamma u epsilon. And since gamma is less than 1, 1 plus 1 over s to the gamma is less than a constant, which depends on gamma, 1 plus 1 over s. Okay? And at the end, you finished with u epsilon here, which cancels this u epsilon, and you finish with constant each u epsilon plus 1. Okay. So where is the big difference between gamma less than 1 and gamma more than 1 is the fact that for gamma less than 1, this is less than 1 plus 1 over s, and you finish here. And if you have gamma more than 1, okay, here you have 1 of u epsilon with some strictly positive power, and you have no a priori estimate. Okay, so that's the main difference. Okay, good. So, but I am in the case gamma less than 1, so I continue. So therefore, u epsilon is bounded in each one 0. I extract a subsequence which converge weakly and almost everywhere. And now I take any function in each one 0, any test function I want, non-negative, and I write the approximate equation. The approximate equation. So here you have weak convergence. Here you pass to the limit. This is free of charge. Okay? And here you have something which converges almost everywhere. So you should prove that f epsilon of x u epsilon tends to f of x u almost everywhere. It's easy when u of x is strictly positive. When u of x is 0, then you have okay, you have to check it, but it's okay. So this converges almost everywhere. Then you have here something which is called Fatou lemma. You have a sequence which converges almost everywhere. Those functions are non-negative. So by Fatou, the inf limit of that is greater than that. Okay? So at the end, you have finished with a gradient u more than f of x u v. Okay, sorry. The integral of a gradient u gradient v is bigger than f of x u v. And for every v, so in particular, since this is finite, this is non-negative, this integral is finite. Okay, so very easy. The problem is that what we want, okay, so I proved the first step in, okay, the first requirement in my definition, okay, that this is finite, but what I want is to have here equal, while what I got is greater than. Okay, so I need a new test function. Okay, the new test function will be the following one. I define the function zeta delta, which is a function from R to R, which is this one. It is 1 up to delta. It goes back then to 0 at the value 2 delta. Okay? So this is not the function like that, but a function like that. Okay? And so this function has a defect that when u epsilon is equal to 0, zeta delta of u epsilon is 1. So I cannot use zeta delta u epsilon test function, but I multiply by phi, which is in each one 0 and L infinity, non-negative. And this is a perfect good test function. I put it in the equation. I have two terms in the left-hand side, a gradient q gradient phi zeta, plus a gradient q zeta prime phi, and this is equal to f epsilon multiplied by zeta epsilon of u epsilon phi. Okay? So here the good news is that zeta delta being decreasing, this term here is non-positive. Okay? And here, since zeta delta is 1 when u epsilon is less than delta, this is bigger than the integral over the set where u epsilon is less than delta of f epsilon of x u epsilon phi. And at the end of this story, this term here, which is the term where the integral can be dangerous because u epsilon is small, this term is dominated by this term here, which is a good term, because in this term, I can pass to the limit in epsilon. This converges weakly in L2. This converges strongly in L2. And so this term here converges to A gradient U gradient phi zeta delta of U. Okay? When epsilon tends to 0. But when delta tends to 0, this term here converges to, okay, you cannot see, but this is true. A gradient U gradient phi, the characteristic function where U is equal 0, because when delta tends to 0, all of that, this pass here, and at the end, you have only the characteristic function of U equals 0. And since U is in each one 0, the gradient of U is 0 almost everywhere where U is 0, so this term is 0. Good. Okay, new break. Okay, so what is the end of the story? Here is the dangerous part of the integral which could explode. But this, the lim sub of this term here, is dominated by something which tends to 0 when delta tends to 0. So, okay, at the end of the day, the things are good because the dangerous term is not dangerous. It's so small that it will not intervene in the result. So the end of the proof is now easy. Okay, you want to pass to the limit. How many minutes do I have? -2? Okay.
7 minutes.
7? Okay, too much. Okay, so I take a test function. This will be in L infinity because I have to use the previous result with phi was in L infinity, but no problem because if you have the result with an L infinity, h1 0 inter L infinity function, you pass easily to h1 0. I write the approximate equation, A gradient Q gradient phi, U epsilon gradient phi. This is F epsilon of X U epsilon phi. And I divide, as usual, I divide this integral in two parts. The part where you have problem and the part where you do not have any problem. The part of you do not have any problem is the part where when U epsilon is more than delta. And the part where you have problems is the part where U epsilon is less than delta. But this part, I showed before that it was small. Okay, is lim sub in epsilon is small when delta is small. So this term actually, when we pass to the limit, first in epsilon and then in delta, the limit of that is 0. Okay? So it remains to pass to the limit here, but this term is not really difficult because f epsilon of x u epsilon phi, when u epsilon is more than delta, by the chapeau, this is less than h of x 1 plus 1 over u epsilon to the gamma, where u epsilon is more than delta multiplied by phi. But this term here is less than a constant 1 plus 1 over gamma delta to the power gamma, which is in L1. We have almost convergence here. We pass to the limit. Thank you. We pass to the limit in this term. We get that. Okay, here there is a trap. If the measure of the set where u equals delta is 0, okay, I pass on this detail, but this is a big trap. But it's easy, it's standard to do it. And this term, so we get at the limit that this integral here tends to the similar integral where epsilon disappears. And then when gamma tends to 0, we tend to the integral of f of x u phi multiplied by the characteristic function of the set where u is strictly positive. So at the end, we finish with this equation, but this is not the good right-hand side. So there is a little subtlety to prove, which is that this term here is 0, and if this term here is 0, so that means that f of x u is 0 almost everywhere, okay, when u is equal to 0. And you look again at the lim sup of this term that I had before. This is the Fatou, the result of Fatou lemma. I had that. I pass here from lim sup to lim inf. And here in this term, I make Fatou, that I didn't do before. And I get that this integral here is dominated by this one. But this integral is bigger than the integral where u is equal to 0, okay? And this tends to 0 when delta tends to 0. So at the end, the work is done. Okay, very good. So when gamma is less than 1, the existence is proved. And actually what we did is more than that. We actually proved a stability result in the following sense, that if I have a family, a sequence of f epsilon, which are all bounded by 1 plus 1 over s over gamma, and they converge almost everywhere in this sense that when I have a sequence s epsilon which tends to s, f epsilon of x, f epsilon tends to f of xs. This is the usual continuity, but this is also the continuity for s equals 0, okay? Which is the only delicate point, because here you can have the explosion. Okay, so we have proved this stability result. Uniqueness is in some sense very easy. Why? Because we are, okay, it's very easy if this function is non-increasing in s. But it's normal, because if f is non-increasing, you will write the equation for u1, the equation for u2, u1, u2, two solution. You will multiply by u1 minus u2, and you will get in the right-hand side this difference. And if f is non-increasing, this difference is negative. Okay? The only point, the delicate point, is that this function could be infinite, and this function here could be infinite. But actually, they are almost everywhere finite, and there is no problem. Okay, so now I will finish with the case gamma more than 1. It is more complicated. Okay. But the method is the same. But the definition of the solution is much more complicated. But the result is the same when you change the definition. So I will take 1 minute to give you the new definition. Okay, the definition, as before, the definition for the solution is in 2 parts. One part is the space. The space before was u is in each one 0 and u is non-negative. Okay? Here this is a little bit more complicated. U is in each one lock. It is non-negative. When you use with the notation of Stampacchia, you use the truncation, and gk is the rest of the truncation. So the function which is like that. Gk of u will be in each one 0, and tk of u will be not in each one 0, but tk of u to some power will be in each one 0. Why? Okay. This point here is easy to understand. What did I do to get the each one 0 estimate in the previous case? I multiplied by u epsilon. if I multiply by u epsilon and gamma is more than 1, I have no good, okay, I have no a priori estimate. I should multiply by something which will cancel the singularity, 1 of u epsilon to the gamma, and this power that I should use is to multiply by the test function u epsilon to the power gamma. But when I multiply by u epsilon to the power gamma, in the left-hand side, I do not get gradient of u to the power gradient of u squared. I get gradient of u to the power gamma plus 1 over 2 in each one 0. Okay? Technical reason, this is not true for u, but this is true for t k of u. And then there is something which was not necessarily in the case where gamma is less than 1, which is to prove that multiplied by a function phi, which is in each one 0 inter L infinity, phi gradient of u is in L2. Okay, essentially this means that the difficulty in this problem is at the boundary. The function u is not in each one 0 because gamma is more than 1, but essentially it is except at the boundary. Oui, Jean-Pierre.
Maximum principle. Inside the domain, u cannot be 0.
Okay, this is a strong maximum principle. Okay? Okay. It's the same.
In 2D with L infinity coefficient, it is okay.
In 2D, yeah, but okay, think about 3D, Jean-Pierre.
3D is if A is C alpha with alpha.
Yeah, but I don't want to have C alpha. And okay, more than that, of course. This is a good answer, and this was the answer given by Luigi, okay, Lucio, Luigi, and Juan. Okay, good guys, of course, but if you want to do that, you pass the word to Juan, and Juan will explain you that. Okay, I was invited, I should present my work. Okay. No, there is another reason, but I will answer the question of Jean-Pierre later. So this is the space where the solution wants to live, and this is the equation. You know, at the end here, okay. So to explain the sense of the equation is minus divergence of A gradient u equals f of x and u. You multiply that by a test function. My test function is v. Okay, so I will ask first that f of x u v is finite. Okay, normal. And then I will ask the fact that the equation multiplied by v is equal to f of x u v. Unfortunately, this has not the usual meaning because u is not in each one 0. So what I do is I use the classical definition of Stampacchia by transposition, which is, by the way, the same as the main tool of the Lyons-Magenès book. Okay, I pass the operator from here to here. I transpose the operator. So this is a okay, and now what I have to do is to, okay, I know where is u, and I know where, okay, I will choose that in such a way that this will be in duality with u. Okay, I already know the space u, so I have just to choose the v such that this is in duality with my space. Okay, the story is a little bit complicated, but let me just describe the answer we gave for choosing the v such that this has a meaning. I take v in a space v, what a notation, which is not negative, and v is in each one 0 L infinity, such that there exists f chapeau, phi chapeau, g chapeau, such that this term here that I want to put in duality with u is written as an element of L1 plus a sum, finite sum of elements which are product of phi by elements of minus h minus 1. Okay, and this allows me, due to the fact that phi, gradient of u is in L2, to define this term here. So this is awful. Okay, I agree. This definition is awful, but the interest of this definition is that it works, and it allows you to make any computation like the previous I did, okay, which were very simple with gamma less than 1. You can do all the computation with those test functions. Okay? It's a little bit messy, but that's good because it will give a long paper. And now I finish my talk,
Thank you very much.
probably in time.
Well, I am going to speak about the spectral convergence for homogenization problems in porous media with roving boundary conditions on the cavities and large absorption parameters. But first I am starting with the stationary problem because this is the natural way in which we have broached the problem since the beginning. In fact, we started studying this kind of problems in 1997 in collaboration with Olga Olejnik and Tatiana Shaposhnikova for linear problems. Then we went on in 2010, around 2010, in collaboration with Tatiana Shaposhnikova for nonlinear problems. Well, this is a work of collaboration mainly with Shaposhnikova, Lobo and Gomez from the University of Cantabria, and Shaposhnikova from Moscow State University. But here are a list of authors that are co-authors or some of the results that I shall expose here. Well, under this general title, homogenization problems in perforated domains with nonlinear roving type boundary conditions on the boundary of the cavities, we consider the asymptotic behavior of the solutions U epsilon of a homogenization problem, this problem, P epsilon. U epsilon satisfies this equation in omega for the Laplace operator. If it's a given function, U epsilon, well, the solution, U omega epsilon is a domain of Rn omega minus the perforations, T epsilon. U epsilon satisfies this Dirichlet condition on the boundary of omega. This roving type boundary condition on the boundary of the perforations. Here we have the normal derivative of U epsilon. Here we have beta of epsilon, which is a parameter, in principle positive parameter, and sigma, a certain nonlinear function that we describe now. This is the geometrical configuration that we consider. Omega domain of Rn with n equal to 2 or 3, T epsilon the perforations that can be placed along over the whole volume in omega, like here, contained in balls, or they can be tubes, like here, or they can be placed along a plane on a inner surface in omega, like here. Epsilon here measures the periodicity, and A epsilon measures the size of the perforations, diameter here and size, radius here, diameter of the sections, transverse sections. Well, they converge towards 0, and this problem arises when studying, when modeling the diffusion of substances in porous media, for instance, and it has been studied by many authors, actually. I mentioned Goncharenko and Kaisu because maybe the functions are closer to our functions, the nonlinear functions, but other authors have considered the problem for different operators and for different geometries. Let us mention Sioranescu and Donato. Let us mention, of course, Conca and Timofte that are here, and many others. Well, these are the functions that we consider. F are a function of L2 of omega, sigma a function of two variables x, u, x in omega, u in r, and sigma is, satisfies this condition. It's a smooth function. It satisfies sigma of x0 equal to 0. The derivative with respect to u is bounded from below and from above by constants. And this condition that seems to be very restrictive is the condition that we use since the beginning for obtaining all the results that I shall expose, but in fact, it can be weakened. For instance, we can allow a certain non-linear increasing to sigma, and also include some functions that arise in absorption process in the literature. Well, the parameters of the problem are epsilon the period, a epsilon the size of the perforations that can be of order epsilon or much smaller than epsilon, and the absorption parameter beta of epsilon that converges towards infinity, in principle, converges towards infinity as epsilon tends to 0. Depending on the relations between these three parameters, we find different relations, different homogenized problems, and we are interested in the critical relations for parameters. That means relations for which we have a different asymptotic behavior from the extreme cases, different asymptotic behavior of the solution from the extreme cases. And the extreme cases are the cases where the solution behaves as if there are, as if all the media is a perforation, or as if we don't have any perforation. Well, of course, as many authors realize in the literature, this may depend, the critical relations may depend on the differential equation, on the boundary conditions, on the geometrical configuration, but also on the parameters of the problem. And this is the situation in our problem. And of course, we are also speaking about the keywords introduced by several authors many years ago, like critical sizes, strange terms, or foreign terms in the literature. Let us mention, for instance, Ciaronescu and Murat, because he's here, I don't know where, but, and also, but also other authors have used or introduced this terminology for different problems. Let us mention also Carlos Conca that are here, but others like Sánchez Valencia, Marchenko and Hruslo, etc. Well, here an outline of the rest of the talk. First, we describe the general situation for the critical relations that we have found for the parameters in the problem P epsilon. We see what this general situation means in the case of perforation by thin tubes. We apply the results to the spectral convergence, and after that, we consider the case of perforations by balls along a plane, and finally, some convergence rates for the eigenvalues in this last case. Well, the general situation that we find is the following. Oh. Well, I forgot to mention here this relation. I am going to mention it now anyway. This critical relation between parameters that I wrote here is a critical relation that I call a critical relation for the absorption that can be read as follows. Beta epsilon multiplied by the total area of the T epsilon is equal to order of order 1. And this provides us a relation between the three parameters, A epsilon, and beta of epsilon. And I call it critical because depending on this relation, when we have this relation or not, the problem, the homogenized problem can change drastically from linear to nonlinear. This is the general situation that we find, as I am going to explain. Here again, the critical relations for the absorption, beta epsilon. Beta, I say that the absorption parameter, beta epsilon, is very large or very small when we compare it with this amount, the total area of the perforation to the power of -1. I say that A epsilon, the size of the perforations, is large or small when we compare it with the classical critical size of the perforations. And when I say classical critical size, I mean that obtained many years ago for many authors for the case of linear problems and Dirichlet condition on the boundary of the perforations. Well, the most critical situation that we find is when we have the critical relation for the absorption parameter, this one, and the critical size of the T epsilon. In this case, the foreign term contains a function h that is a nonlinear function that is obtained implicitly from this equation, this functional equation, where C is a constant that depends on the geometry of T epsilon, on the dimension, on the dimension of the space, and on the constants arising in the relations for the parameters. And sigma here is the original, the function of the original problem. Well, what we show is that H is unique and has the same properties of smoothness of the original, of the function of the original problem, sigma. This other case, when beta of epsilon is satisfies the relation, that is when we have the critical relation for the absorption and large sizes of the perforations, then the strange term is obtained like a constant multiplied by sigma, the function arising in the original problem. This case is also of great interest because for beta of epsilon fixed, we obtain a critical size of the perforations. And for A epsilon fixed, we obtain a critical size of the absorption. Well, anyway, the homogenized problem is nonlinear. Well, in this other case, when beta of epsilon is very large, and we have the critical size of the perforations, then the homogenized problem is linear, contains the foreign term that does not depend on the sigma of the original problem. Other extreme relations for beta of epsilon and T of epsilon different from these relations, for beta of epsilon or A of or the size of the relations different from these cases, can imply that the solutions do not take into account the perforations or the absorption parameters. Let us consider what these relations tell us in the case of a domain perforated by thin tubes. Here the geometrical configuration of the domain, omega this cylinder, G epsilon are the tubes, they are A epsilon G times 0L. Here we have the periodicity cell, the section, the transverse section of the cylinders is of size A epsilon. Epsilon, okay, to A epsilon. Epsilon is the distance between the cylinders. Here we have the projection of the section of the cylinders, of the basis of the cylinders, and of the omega, that is the basis of omega and the basis of the cylinders on the plane, x1 equal to 0. We see a periodical distribution of the cylinders, of the transverse section of the cylinders in the plane, but it can be not so periodically like here. Well, anyway, in this case, we have the following. The homogenized problem is this one. Sigma is the foreign term arising in the partial differential equation in these cases, for all these relations between the parameters. Sigma is defined implicitly, or is defined through a function, h defined implicitly from this functional equation through sigma. In the case where we have the critical sizes of the perforations, of the cylinders in this case, and the critical relation for beta epsilon. In this case, this relation read beta epsilon, A epsilon, epsilon to the power of -2 converge towards some positive constant, and epsilon square logarithm of epsilon converge towards some finite constant different from 0. Well, in this case, the h is obtained implicitly. For the case where we have very large size of the cylinders and the critical relation for beta epsilon, in this case, the foreign term is obtained like a constant times sigma. The original sigma is the function arising in the original problem, and in the critical, in the case of critical size of the perforations of the cylinders, transverse section of the cylinders, we have this case, and large absorption, we have this foreign term that depends on U linearly, but not on sigma, independently on the data. While the other stream relations are beta epsilon very large, and beta epsilon very large, and the sizes of the cylinders very large, then u epsilon is approached to 0, or beta of epsilon very small, or the sizes of the cylinders also very small, and then in this case, the homogenized problem is the Dirichlet problem in omega. Well, since we want to consider spectral problems, we consider the case in which sigma is depends linearly on u, sigma of xu equal a of x multiplied by u. In this case, all the homogenized problems are linear. The foreign term depends on u linearly, but depending on whether we have the most critical relation, the relations for the critical relation for beta epsilon and the critical size of the cylinders, or we have other critical relations. Depending on that, the foreign term depends on a of x linearly or not. That means in this h is the function, the solution of this equation that in the linear case can be solved explicitly. Then it depends non-linearly on a of x. And in the rest of the situations, when we have the critical size for the critical relation for the adsorption and the perforations very big, then we have a linear dependence on a of x and on the foreign term. I am speaking about the foreign term, a linear dependence on a of x. And in the case where beta of epsilon is very large, and we have the critical size of the tubes, then there is no dependence on the strange term, but still there is no dependence of the strange term in terms of a of x, but still we have a foreign term, a strange term. Well, I have tried to gather all the possible situations, all the possible limiting problems in this figure. It is a general description quite general, of the homogenized problem that we obtain. But since we have very many possibilities for the relations between parameters, I have to choose some of them, and I choose a epsilon equal epsilon to the power of k exponential of minus alpha squared epsilon to the power of gamma, beta of epsilon to the power of 2 minus m epsilon exponential of alpha squared divided by epsilon to the power of gamma. Gamma, m, and k here are 3 parameters that I take to be the axis here, m, k, and gamma. The case of the critical size for the perforations is here in this plane, gamma equal to 2. The case of the critical relations for the adsorption is here in this plane, k equal to m. Here we have, in the intersection, we have this line in red that is where we have the most critical situation the most critical relation between parameters. The function h arising in the homogenized problem, the foreign term, is defined implicitly from the sigma. In this case, for the critical relation of beta epsilon in this plane in red, we have the homogenized nonlinear problem, but directly from sigma, constant sigma. When we have the rest of the situations, well, here, in the rest of the situation, we have here in this part in green, the homogenized linear problem independent of sigma, and when beta of epsilon very large and t epsilon very large, u epsilon approaches through 0, and if beta epsilon very small or t epsilon very small, we have the Dirichlet problem in omega as homogenized problem. Well, a scheme of the kind of convergence of the correctors that we have, but let us apply the results to the spectral convergence. We have here the associated spectral problem in the case of linear sigma. sigma is beta of epsilon A of x times u epsilon, lambda epsilon the spectral parameter. This problem, as well as the rest of the problems, the spectral problems appear have a discrete spectrum. For fixed epsilon, the eigenvalues converge towards infinity. The eigenfunctions suitably normalized are basis in L2 of omega and H1 of omega epsilon. And we apply, to obtain the convergence, the spectral convergence, we apply the result on the convergence of the spectrum with conservation of the multiplicity for operators of Hilbert spaces, depending on a small parameter. That means that we have to put our problems, our spectral problems, in terms of operators on Hilbert spaces, satisfying certain properties. We managed to do this and to verify all the properties of these operators. Stated in a theorem that I know from the book of Oleigny, Shamaev, and Yosifian. But mainly what we have to show is similar to what we have shown for the stationary problems, for the convergence of the stationary problems. Roughly speaking, to summarize the theorem, I would say convergence of solution of stationary problems of P epsilon in H1 of omega weak means implies the convergence of the eigenvalues with conservation of the multiplicity, and also, of course, this implies also a convergence for the eigenfunctions in H1 of omega weak. If we want to get bounds for discrepancies between the eigenvalues, we need to estimate to have bounds for discrepancies for the solutions of the stationary problems, u epsilon minus u0, in the suitable topologies, and this implies sometimes obtaining correcting terms, and this can be noisy in the topology that we need to do it. Anyway, in the case of cylinders, we managed to show the convergence with conservation of the multiplicity of the eigenvalues of P epsilon towards the eigenvalues of the homogenized problems, with the foreign term arising here in the equation, as we explained previously, depending on A of x linearly or non-linearly, depending on all these relations. We are here in the case of perforations by bolts along a plane. The geometrical configuration of the domain is also classical. We have omega divided into two parts by omega plus and omega minus by this plane, by this space inside omega sigma, where we put the perforations that now are bolts. For the dimension 3 of the space, the results are also obtained for upper dimensions. But now we have the absorption parameter epsilon to the power of minus kappa. The radius of the perforations epsilon to the power of alpha. That means, and the distance between them, of course, as previously, epsilon. This is the geometrical configuration. We have two parameters, kappa related with the absorption, alpha related with the size of the balls. And here, just to mention that the critical size now, the classical critical size is given by the A epsilon that I call it also here R epsilon, the size of the perforations of order epsilon squared. And the critical relation for the absorption is given by this relation that gives us a relation between kappa and alpha. And this relation means that kappa equal to alpha minus 1. This is the case of the critical relation for the absorption. And the homogenized problem also contains the foreign term A of x, but now on the, as happens usually, on the bound, on the surface sigma, where we have the bolt. But also now it depends on A of x linearly or non-linear. This foreign term depends linearly or non-linearly depending on the relations between the parameters. The most critical situation is here now when alpha equal to kappa equal to 2, and here we have a non-linear dependence on A of x of the foreign term. Here in this line in red we are in the case of critical size for critical relation for absorption, we see that, well, excuse me, alpha and kappa now are the two parameters related with sizes of perforations and absorption. And then in this line, we see that for fixed alpha, we have a beta. Well, for fixed alpha, we have a kappa that gives a beta of epsilon perfectly defined in such a way that the behavior of the solution changes from the Dirichlet problem, the homogenized problem, which is the Dirichlet problem, to nonlinear dependence on A of x, to the Dirichlet problem in omega plus, omega minus. And these cases are, well, here, excuse me, we have also the critical, a critical relation, but this is only for the perforations. The limiting problem is the homogenized problem with the foreign term not depending on A of x. And the other extreme cases are Dirichlet problem in omega or Dirichlet problem in omega plus union omega minus. We can extend the result for the dimension n greater than 2. Also, we obtain this kind of results for the non-linear problem, stationary non-linear problem, for the dimension 3, for upper dimension. Here, in this case, in the case where alpha equal to kappa equal to 2, we have the most critical situation where we have the foreign term defined through the nonlinear equation, implicitly defined from the functional equation. Well, a sketch of the convergence. Finally, in this case, we managed to obtain bounds for convergence rates for the eigenvalues and the eigenfunctions. In fact, we also have the convergence with conservation of the multiplicity, but the bounds for discrepancies read as follows. The kth eigenvalue of problem P epsilon minus the kth eigenvalue of the homogenized problem smaller or equal than ck epsilon to the power of 1 over 16, and the same kind of bounds for the associated eigenfunctions. Now U is an eigenfunction associated with the eigenvalue lambda k, and U epsilon is a linear combination of eigenfunctions associated with eigenvalue lambda k epsilon converging towards lambda k. And this is for the case alpha equal to kappa equal to 2, but we have similar bounds for the rest of the cases. I think better I don't put here. Then I just want to finish, if it is possible, for being insisting, thanks to the organizers for the, well, it has not sound, sorry very much. Thanks to the organizers for the organization of your 60th birthday. And also I would like to quote this song that I learned from one of the first, the quote to this song that I learned from the first paper that I read on homogenization, more or less one of the first papers. Well, thank you very much to everybody. Thanks.